Hello and welcome back, folks. Huge myriad sea of faces. Jake, how's it going, Jake? All good. And Isabella's there again. That's fantastic. My gosh, a whole lot of new faces as well. If you're live and you want to sort of say hello and start your face cam, that would be absolutely fantastic. And about 2 or 3 times during the course of this thing, I'll put a live chat thing going, so you can answer questions and ask questions and stuff like that as we go through. So I'll just take off 1 or 2. There's a couple more faces in there that I haven't seen. So Dylan, I'll just say, and Eunice, hello Eunice, and Bryce, hello Bryce. And a couple more faces I can see. So Claire and Bryce and Emea, hopefully I pronounced that well. And then Matthew and Isabella. I've got Victoria and Dylan. So sorry if I haven't got you all. And Super Black Family, fantastic. Tennessee Potter, cool. And I've got to get the chat going. So if you don't want to go live, I've got the chat button on the right, Dylan from Suffolk. So you can put some chat in there, etc., and that would be great. So welcome, my name's Dan, and welcome to MEL Chemistry. And this box set today we're doing is Oxygen. Oxygen. Okay, cool. Still doing the experiment from yesterday at the end. Yes, for those students who were yesterday, where we did the copper experiment, I'm going to end with the copper experiment. So for those of you who haven't seen or haven't done the copper experiment, I'm going to end with that one because it has to work over about sort of 48-hour period. So don't panic. So it's a little bonus bit for you guys at the end. So you can see some copper. Ella says, I'm in France, but Scotland. Hello, Ella. Yes, cool. Excellent. Right. So without much further ado, now one small apology. Normally I have some little slideshows to show you a little bit of the chemistry, etc., but for some reason I'm uniquely gifted in bringing little techno gremlins into the situation, and the slideshow ain't working. So I shall provide a prolonged opportunity to ask questions, etc., on a technical basis throughout the course of this video, and then next week, hopefully, the video. Sorry, week after next, the slides will be back. Okay, so if you're ready, let's go through the bits and pieces that you need. So I'm going to swap my camera focus. And evil frogs, Andrew, yes, the evil frogs are with us in person. They are indeed. Jay. Right, cool. So what do you need? You need some hot water. So I've got some hot, doesn't have to be boiling water, but it does need to be hot water. Okay, so hottish water, if you've got access to that. I've just got it in a flask because I'm not near a tap at the moment. You do need peroxide, so your peroxide solution for the oxygen, so peroxide, that can be 3% or 6% peroxide. Hi, Bryce. Right, and for the first experiment, obviously you need your glasses and you need your gloves. For the first experiment, we need the following chemicals. You need your methylene blue. So methylene blue is the first one. So the first one we're going to do, I'm so sorry I didn't do that, how very rude of me, is the blue bottle experiment. So this is the first experiment we're going to do, blue bottle, okay? So you need the methylene blue for that. You also need the lactose. If you've ever heard the word lactose before, of course this is the sugar that's found in milk, so sugar, milk sugar. You also need the calcium hydroxide, if you've got calcium hydroxide. You need 1 little flask. So flask. Now, hi, Isabella, you got a question? Isabella, you need to ask to unmute. Isabella, have a, yes. Isabella, you had your hand up?
Yes, sorry. So I don't have lactose.
You don't have?
Lactose.
You don't have the lactose at all? If you don't have the lactose, if you can use a glucose solution, if you've got a bit of glucose, you can use a glucose solution if you haven't got the lactose. Okay, cool. Right, I've got another little hand up. Louisia, yes. Louisia, yeah, hand up. Louisia, gotcha.
My name is Leo. Before you start, is the time machine real?
Leo, Leo, is what real?
Time museum.
The Time Museum?
Time machine, he's asking.
Oh, a time machine. Not yet. But Einstein, if you look at Einstein's theory of relativity and special relativity, what the theory of relativity suggests to us is that we can theoretically go forward and backwards in time. But at the moment, there are no such thing as time machines, okay?
we don't have lactose.
If you don't have lactose, you can use glucose or dextrose, okay? If you don't have lactose, you can use, if that's in your house, if it's for some reason, sometimes a chemical won't appear in a kit. for whatever reason. Now, if it doesn't appear, guys and girls, if you have a kit with missing chemicals, please, 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 Isabel, if you've got 2 glucose in the kit, yes, use glucose. Use glucose. If you haven't got the lactose, use glucose. That's perfectly fine. Yep. Okay, that's a workaround. Right, cool. You also need a bung, so you need to make sure you've got a bung in your kit. Eunice, raise hands. Eunice, where are you, Eunice? I can't see you. Oh, yes, yes, Eunice. Yes, Eunice, how can I help?
Hello, can you hear me?
I can, yes, go for it.
I don't have hydrogen peroxide.
If you don't have hydrogen peroxide, now that is something I can't help you with, because you definitely need, for the first experiment, you definitely need or for the second experiment, you need the hydrogen peroxide, okay? So don't panic.
Is that supposed to come in the kit?
No, if you are in the UK, we can't transport the hydrogen peroxide. In America, they can. But sometimes the hydrogen peroxide, because it's quite an unstable chemical, it breaks down to water and oxygen, so it's not a problem. But you can find this in any pharmacy, and just ask for hydrogen peroxide solution, and they will give you one that works. Okay. And this video, this clip, you can get it from Monday afternoon onwards. Is that okay? But we can do one of the experiments. We'll do the blue bottle one, if that's okay.
Yep.
Is that okay? Nice one. Thanks, Eunice. Thank you. Yes, got another hand. Dylan. Dylan, you got a question? Dylan, you've got to unmute yourself. Oh, keep your gloves on, keep your gloves on. Yep. Dylan?
What type of thing do you need?
Oh, bung. The bung that you need is the solid bung, so no holes in the bung, okay? So there's a no-hole bung for this one, all right? All right, guys? On that note, ladies and gents, we'll crash on and conduct the experiment. Now, I haven't got any gloves on and I haven't got my glasses on, so that is what's happening next. Okay, so cool. So gloves and glasses. And what we're going to do first, we're going to do the blue bottle experiment. This is a really wonderful experiment. Actually, they're both really wonderful. Right, so gloves and glasses. Oh, quickly get me gloves on. Now, once again, apologies that I haven't got the slideshow going, but again, I will pause after each experiment and explain chemistry and what's going on and why we're talking about oxygen. It's in fact one of the most important elements, of course, in the universe. It's the 3rd most popular element in the universe. So after hydrogen and helium, oxygen is the most common element in the universe, which is why we're playing with it today. Right, so let's move those out of the way. So first things first, you get some warm water. Get some warm water, get your filter funnel and pop it into your flask. So get some warm water, pop your funnel in a flask. And we want 40 mils, you want 40 millilitres of warm water in the flask. So 40 millilitres. And if you look at your flask, it's the very first line on your flask. The 40 mils is the very first line on your flask. So pour your hot water into the flask, in a conical flask, so 40 mils. If it's slightly over, slightly under, don't panic too much, but about 40 mils into your flask. And of course, yeah, 40 mils, that's lovely. Okay, now next, if you've got glucose or lactose or dextrose, now my one's got lactose in my kit sometimes, you then take the whole bottle. Now remember, you've got to depress the little tiny safety plug out of the top of the neck of the bottle, okay? So depress the safety plug. So give that a little tiny push, a little bit of a wiggle. Sometimes they're quite stiff, so you've got to be quite persistent. Okay, so give that a little tiny push like so. Now you want the whole bottle of that, guys and girls. Okay, the whole bottle needs to go into the conical flask with your warm water. So the whole bottle, okay? So squeeze the whole bottle in there. Okay. Now once you've got the whole bottle in there, give that a little tiny swirl around. So just give that a little swirl to mix it around, okay? Is that all right? So a whole bottle in there. I don't have it also. Robert, if it's glucose syrup, glucose syrup rather. It might be glucose solution, it might be dextrose solution or lactose. So either one of those will do absolutely fine. Okay, so once you've done that, the next thing we need to do is put just five drops, and be very careful with this, of the methylene blue. Okay, so 5 drops of the methylene blue. And again, just depress the little tiny safety plug out of the neck of the bottle. And so 5 drops only, okay? So 1, 2, 3, 4, 5. So 5 drops only into the bottle. Sorry, how much glucose? Martin, the whole bottle, the whole container, Martin, of the glucose. I'm confused about lactose. Chantal, was that supposed to come in the kit? Yes, the glucose or the lactose or the dextrose should have come in the kit, Chantal. And it should have come in a little yellow pot, okay? So how much good? Yeah, okay, cool. So now you've got a sort of blue solution, a nice blue solution, okay? Now, this is very important, we've come to the calcium hydroxide. So the calcium hydroxide, so this is an alkaline. Okay, so give it a little tap. Now you see your spoon has got a large side and a small side. You want a small side, so use 2 small sides. Did you V? Ella. Okay, so 2 small even scoops. 2 small even scoops of the calcium hydroxide. So 2 small even scoops of the calcium hydroxide. So relatively even. Okay, so one of those goes in. 1. And then 2. So 2 small scoops of the calcium hydroxide in there like so. Okay. And now we're going to start with a little bit of magic. So we've got a blue solution in here with a little bit of calcium hydroxide. And I've got my blue solution here. And what you're going to do now is give that a nice little swirl. Like so. Let's give that a nice little swirl. Do we put all the lactose? Yes, Katie, you put all the lactose in, no problem at all. Did you see the end of the calcium? Ella, you put 2 small scoops, 2 of the small ones in there. So I've just done that now with my bottle. I've just given it a swirl, and if you count, I think maybe about 10, 9, 8, 7, 6. But we just count a little bit. That's a nice blue solution. But hey, look! Oh my gosh! Something magical. Oh! Got some questions.
I don't have calcium hydroxide. I have sodium hydroxide.
Yes, if you've got sodium hydroxide, perfect, that will do fine. So sodium hydroxide and calcium hydroxide would be perfectly fine. Yeah, they both work, they both do the same thing. Oh my gosh, but my blue has disappeared. And so, if you get your blue again, if you get your colour solution, nice one, Jake, lovely, jubbly, lovely. Give it another shake, and voila, sit back. The blue has returned. So my blue has returned as if by magic, and I didn't do anything. Too fast. Lincoln, if you don't have the calcium hydroxide, you should have the sodium hydroxide, I think. Ella, you're quite correct. It's not magic, it's pure chemistry. You don't need magic, you just need chemistry. So I'm going to hold that up. What comes after the lactose? The calcium hydroxide or the sodium hydroxide. I'm going to put but my blue is disappearing. Oh no. Okay, so that's disappearing again. Cool. Has everybody worked? Can I see everybody's? Has everybody worked? How's everybody going? A colourless solution, not quite. Blue solution, it hasn't worked just yet. Might just take a bit. Remember, yep. And we've got Super Black Family, fine. Working. Dylan, fine. Andrew, Jake's fine. Isabella, Martin. You might take.
So we got held up because we didn't have the calcium hydroxide. So the sodium hydroxide is liquid. We added 2 little scoops of the liquid.
Yes, sure. It's 2 scoops should do that fine.
And then nothing's happening.
Now this particular reaction is very sensitive to a number of things. So it's very sensitive to temperature, particularly sensitive to temperature. And if the volume of water slightly changes things a little bit. And also the methylene blue, if you put a little bit more methylene blue in, that tends to it might take a little bit longer. So just give it a shake and then just be patient, just wait patiently. Now, if it doesn't go, Isabella, a couple of seconds, and if it doesn't go after about 2 to 3 minutes, then what I suggest you do is do it again, wash out your flask, do it again, but this time make the water super hot, okay, super hot. Is that okay?
Yeah.
Cool. Isabella. Asked to unmute. You've got to unmute yourself. Isabella.
Okay, so, we tried 2 small scoops too, but in the instructions it says 3 big spoons.
Okay, sorry. Are you using sodium hydroxide?
Yes.
Okay, yeah. Depending on the molarity, that one I haven't seen the molarity of that one. But if the molarity is, Super Black Family is working. Give it a good shake now. Give it a good shake, and you'll be fine. Big shake, big shake. Isabella, use the 3 shakes, 3 big scoops that it tells you, okay? Not the 2 small scoops, okay? And then it will work, yeah. Ask to unmute. Who are Ella? Yes, Ella.
Mine In my booklet thing, it says 3 big scoops instead of 2 small scoops.
Yeah, Ella, if your booklet says 3 big scoops, it means you're using the sodium hydroxide solution. So please use the 3 big scoops. Okay. Is that okay? And it'll work. And it will. I promise you it'll work. Everybody else okay? Imea, got your hand up. Imea. You got your hand up. Imea. Imea, yep. You've got to unmute yourself there.
We don't have a question.
Oh, you don't? You were just putting your hands up. Well, if you just put your hands up, you're going to fool me. Okay, cool. Right, so I'll just check if there's any...
love this.
Hey, is this cool or is this cool?
Cool.
Yes, this is Magic Chemistry. And again, you see, once again, I've got to colour this one, but you know, I prefer my solutions a bit bluer than normal. So give it a good shake, and voila. So what's actually happening here? If I just change screens a little bit, and hopefully I can explain. Sarah and Dylan. So Sarah, sorry, Dylan, I've got a question. Yep, I'll answer your questions. Yep. Oh, and hang on, I've lost my screen. There we go. Jake, you got a question?
What's the science behind this?
I'm just going to explain that just now, Jake. I'm just going to explain that just now. Dylan?
For some reason mine is still a light blue.
Did you have the sodium hydroxide or the calcium hydroxide?
Green.
You had the green one. How hot is your solution?
Quite warm.
It's quite warm. And you put 5 drops in. And only 2 small scoops. And did you have the lactose or the glucose?
Lactose.
And you had the lactose. It might just be you just got to give it a couple more minutes, okay? And you shake it quite violently. Yeah, so just give it a couple. Sometimes you've got to be a bit patient, Dylan. Okay. Okay, let me explain. In it works. Lovely, fantastic. Eunice's works, Martin's works. Isabella, I hope yours is getting to work. Let me explain then some of the chemistry here for you. Now, I'm so sorry that I don't have the slides to show you. So basically, you put the methylene blue, and it was blue, into the solution, okay? And that's fine, that's perfectly fine. But if it loses some electrons, so remember all molecules and atoms, if you lose an electron or gain an electron, you become charged. You become things called ions. And that changes the nature of the chemistry. It changes the nature of the chemical. So in here, what we've actually got is the methylene blue is being robbed of some ions. It's changing its nature. So it's going into colourless. Okay? And when it gains back some electrons, it then goes back to blue again. But what's doing that? When you shook, what is in the top bit of the conical flask? What's in the top of the conical flask? Anybody? You can maybe type it in. It's worked. Tony says it's worked. Yes. Eunice asked to unmute. Oxygen. Yes, there's air in here. And oxygen is what's called, it has a very powerful property called an oxidizing agent. So it rips electrons away from things. So it rips electrons away, and that changes the nature of the chemical property of the methylene blue. But after a while, look, everything's settled down again. Okay, so you've got sugars in there donating some electrons. You've got methylene blue taking the electrons, and then the oxygen taking the electrons off the methylene blue. And that reaction goes backwards and forwards. Okay, it goes backwards and forwards. And you see my flask is going slightly colourless. And that reaction's settling back down again, and the oxygen is quite happy, but there's more oxygen in here, and so we can strip the electrons away from the methylene blue again, ba-ding, and then back to blue. So it's one of those classic reversible reactions. Is that okay? How's that? I'm so sorry I don't have the slides to sort of show you so you can see it a bit more physically, so little models of oxygen and atoms and molecules and stuff like that, okay? All right, cool. Before we get on to the next one, does anybody know what percentage of oxygen is in? Cool, it's worked. I see that, Martin, excellent. Does anybody know what percentage of oxygen is in your body? Jake, working a tree. Does anybody know what percentage of oxygen is in your body? Ask to unmute. Eunice, yes. Eunice.
Hello?
Eunice, yes, go for it.
No, just asking, what would happen if you decrease the amount of methylene?
That's a fantastic question. If you decreased the capacity of the liquid itself to snatch away electrons, you will lengthen the time that it takes for that reaction to sort of take place. Okay, try that.
Yeah.
Now, in the nature of chemistry, in the nature of MEL, you must try that yourself. So experiment separately and see the difference in time. If you keep all the other variables the same, the temperature, the volume, etc., and then just change the one thing, which will be the number of drops of methylene, that's your experiment, okay? So try that and then come back to me. Is that okay? Super black.
And also,
sorry.
And also, what would happen if you decrease the amount of methylene in your?
That's the question you just asked me, I think.
No, I asked you how much water.
Oh, I thought you said methylene to start with. Oh, the water itself actually really just acts as the mechanism, the vehicle through which to have this reaction sort of taking place. So even if you set down to 20 or we went up to 50, what effectively you would do, if you went up to 50, for example, you just reduce the amount of oxygen in the flask that the whole reaction has access to. So that would decrease the time as well. And then if you reduced it, that would increase the time. So what you've got to do is just have a little experiment. There's a great questions, absolutely beautiful. So control those variables and then see what data you get. Is that okay? Nice questions, I like that a lot. Super Black Family, yes, asked to unmute. Gotcha.
Is it 80% in the body?
That's not far off, you know. That's not bad. It's actually about 62%. 62% of all that you see here and now is oxygen. How's that? So this is a really important element. That's why we've got an oxygen box. So at 62% of your whole body is oxygen. And of course, we no need to breathe. That's all very good. And that's going into our oxyhemoglobin, and that's all really good. But you're about 60 odd percent, 62% oxygen in your body. So it's a really important element. That doesn't make that you're a big gas bag. It means that all the muscle and the tissue and the bones and stuff like that is made of oxygen. So for example, does anybody recognize what this is? Anybody recognize what that might be? Any of you guys budding mineralogists? I've got a hand. Where that hand? Mackenzie. Yes, ask to unmute. You've got to unmute yourself.
A clouded quartz.
Hey, that's a lovely. You got clouded in there as well. Proper mineralogist. It's actually a bit of pure quartz. It could be clouded. It's just probably the video footage. But this is pure quartz. It's one of the most on the surface of the Earth, the crust of the Earth. It is one of the most common of all of the crustal compounds. And this is silica oxide. The next most common one here, you probably can't tell what that is, but that's a bit of limestone. That's one of the most popular parts of the whole of the crust. And that's calcium carbonate. So O3 in there. Another big chunk of this, as you probably recognize, is a granite. And about a third of that is oxygen. So nearly everything on the Earth, everything, near enough everything, has got oxygen bonded to it, welded to it, etc., etc. So this is a super important element. Got another question. Veronica Gonzalez. Yes. Ask to unmute. You got to unmute. Veronica, yes, go for it. Yep.
This is my name because my grandma walked me into this.
Sure. What's...
So, and how is everything in the world? How does everything in the world have oxygen in it?
That's a lovely question. How does everything in the world have oxygen in it? This is a very complicated problem. But if I can shortchange, if I can make a very complicated answer to that, but if I can make it real simple, what actually happens is all the elements, can you see all the elements behind me on the periodic table? So there's here, about 119 of them, all right, we don't really have ones down here, we've only got a couple of atoms of the new ones, but the majority of them all come from stars, okay? They all come from stars. So when you see a star like our sun, when they go kaput and they turn into a supernova and they go bang, okay, and they throw all of their guts out into space, all of that big bang and all of the elements that make up the whole thing. So everything on Earth, every single thing on Earth, including you and everything that makes up you, ultimately comes from a star or a series of stars, okay? They're called supernovas, where all of these elements are made. As I said to you, a third of all of these elements, a third of all these elements is oxygen. And oxygen is very, very, very reactive. So as soon as oxygen gets together with any other element, and here, I don't know if you can quite see it, but here's a piece of elemental silicon, pure elemental silicon. And as soon as you get silicon reacting with oxygen, that's gas, is white gas, you get silica oxide, you get glass effectively, or silicates. And then the silicates can react with other elements, etc., etc., etc. So what then happens over millions and millions and millions and millions of years, when all that sort of dust and dirt and stuff like that from space starts to coagulate and combine to form planets. This is a long story, complicated story produced into a sort of snapshot. Eventually, then over time, all these chemical reactions evolve to form all sorts of different other compounds. And in time, we find things like amino acids and proteins and stuff like that. And then we get sort of human life and all that kind of stuff. So I'm not sure that was the best short snip look at the whole of chemistry of the universe. But hey, I can answer more questions a little bit later. Okay, cool. Shall we do experiment number 2? Everybody ready for number 2? Yep. Hopefully everybody's ready for number 2. Right, cool. So for number 2, I'll just give that one last little shake. I'm going to swap my screens. Hang on. Swap screens and change the focal point. Okay, so here we go. So give that one last little shake just for the sake of it. Now that will last for more or less the whole of the day. If we then, for this experiment number 2, we need the... Louisa, one last question. Yes, and I got Roberta C. Sorry, yeah, sure. Louisa first. Yes, we're going to burn pure oxygen. We're going to burn pure oxygen. Yes, Jake, yes. That's the next one. Yes, Louisa, you're on. You got to unmute yourself.
Go ahead. What do you want to ask?
So, did a goid came from a volcano?
Goids.
Goids.
A rock that come from a volcano.
Oh, and the stuff that comes out of volcanoes depends on the type of volcano. So you get basically very silica-rich volcanoes and then increasing or decreasing amounts of silica. A lot of volcanoes that you'll be familiar with are basaltic volcanoes. If you give me 3 seconds, I'll just quickly go and get you a bit of basalt. So this is a bit of basalt that comes out of volcanoes, and that's magnesium or iron magnesium silicates. There's loads of oxygen in that. That's a bit of hard basalt that comes from the ocean floor. So all of the ocean floors in the world are made of basalt, and that's got lots of oxygen in that too. Okay, so yes, volcanoes are a massive source of molten rock, and they all contain oxygen. Yeah. I've got a hand up from Robert. Robert.
I don't have hydrogen peroxide.
Robert, if you don't have the hydrogen peroxide, you can't do this one now, but if you watch me, this video will be available to get about tomorrow, sorry, a little after tomorrow afternoon, but you can get the hydrogen peroxide from any chemist, so any chemist anywhere at all. It's Sarah, question. Yes, it's Sarah. I can't see you on the screen, it's Sarah, so you're on a different one. It's Sarah, where are you? Can't see it, Sarah. Where are you? Oh, hand up. Yes, sorry. I'm doing it. Unmute. Inna. Yes.
I got a question. So, for the second experiment, do we have to wash the flask?
Yes. If you could just quickly, for the second experiment, if you just quickly give the flask a quick rinse, that would be perfect. Yeah. Cool. And no more questions yet. Cool. Then I shall crack on. Excellent. Ishan. I've got a question from Ishan. Yes. Ishan and Nick. Hello, Ishan.
So is there anything in the world that's just a pure element without any oxygen?
Yes, there is. Yes, of course. And as I showed you before, this little thing here, this little object, is pure elemental silicon. So that's the element silicon, Si, behind me on a periodic table, if you look. And there's no oxygen in that at the moment. So all the pure elements have no oxygen in it. And of course, there are lots of compounds that don't have oxygen in it. There's just not very many. It's a pretty aggressive reactive element, this one. Okay, cool. So without much further ado, let's have, if you've got your flask handy. Now this is really good to do it in the dark. So do it in dark. I know that Sarah, you said a difference in alkalis and acids. I'll answer that at the end if that's okay, Sarah. And Eunice, if you just give me a couple of seconds, I'll get to you at the end. Is that okay? Cool. Right, I'm going to turn the lights down a little bit here because this is best done in the light, in the dark. Now you do need some matches or a lighter. So you do need matches and a lighter for this one. Now the chemicals that we need are manganese oxide. So you need your manganese oxide for this one. This is the black one. Now you don't need very much of this powder. You just need a small scoop, okay? So for this one, you just need a very small scoop, one small scoop, all right? If you get your filter funnel again, so get your filter funnel and your peroxide solution. So let's get our peroxide solution, and you want 40 mils, so 40 mils. It's the same volume of hot water as you almost used in the previous experiment. So use 40 mils of hot water of peroxide. Hi.
On my thing, it says to use 1 bottle of this.
If you have peroxide, yes. So sometimes the boxes come with peroxide. If your box came with peroxide, everybody else, yeah. If your box came with peroxide, hydrogen peroxide, H2O2, use the whole bottle. So use the whole bottle, okay? So my kit here is in the UK, and it doesn't come with peroxide. So I have to buy the peroxide from a pharmacy. I think Eunice, one of the students on tonight, you didn't have it because you're in the UK. So you can buy that from a pharmacy tomorrow. So you can look forward to that tomorrow. We don't. Katie, if you got kitters in the UK, you might have got the peroxide, so you have to buy it from a pharmacy. Any pharmacy will have a peroxide solution, okay? Needs to be about sort of 2-3%. Abigail, yes, quick question. Yep. Abigail. And Mikla, yeah. Go for it.
Okay, so how much do we pour of hydrogen peroxide?
If your kit came with a bottle of the hydrogen peroxide, you put the whole bottle in, okay? Is that okay?
Thank you.
You're very welcome. It's a pleasure. Yeah, 2 more questions. Asked to unmute. Yes, Harrison. Yeah, Harrison.
How much hydrogen peroxide did you say?
If you have a kit that's got the hydrogen peroxide in
I
it.
was just emptying my flask for it.
I'm so sorry, say that again.
I was just emptying the flask to do it.
Oh, you had. So your peroxide came separately, did it? In a bottle?
Yeah.
Yeah, if you put 40 mils. 40 mils.
14 mils, okay.
Yep, you're very welcome.
Is it 40 or 14?
40.
40, okay.
Correct. Hi, Eunice.
Sorry about that.
No problems, no problems. Hi, Eunice.
Hello. Just coming back to oxygen being in like most elements, yeah. Like how does oxygen actually enter into the materials and elements?
That's a fantastic point. It doesn't enter the materials, elements as such, Eunice. What oxygen does is it binds chemically, it reacts chemically like everything else. In the periodic table behind me, all of these different elements react chemically. And so what things do, they either take electrons or share electrons with any other element. And I'll spend a little bit more time with that at the end. But oxygen is a particularly aggressive oxidizer element. It will react with practically everything. Okay? Okay, cool. Right, so I've got my peroxide in my flask. I now need 1 small scoop of the manganese oxide. So 1 small scoop of the manganese oxide. It's a good idea at this point, if you're working with somebody, a team or a teacher or a parent or something like that, it's a good idea at this point to have your splint handy. Okay, your splint. Is it going to be jokes? Ella, there will be jokes. Of course there will be jokes, Ella. Sorry, I've missed a few because the slides are missing. But I'll tell some jokes at the end, if that's okay, Ella. Right, so what you need to do, can I just point this out? Isabella, quickly. Yeah, Isabella, unmute. Isabella.
Okay, so it taught on the instructions it says to add a whole bottle. So do I add a whole bottle?
Yeah. Yeah, if you have the peroxide in a bottle, you add the whole bottle, okay?
Oh no, the manganese.
Is that a liquid? Is it a liquid?
No.
If it's a solid, you just need 1 small scoop.
Okay.
Okay? Right, now watch me carefully. This is very important. Very important. Right, I'm going to light this. I'm going to set alight this spill or this splint. So in chemistry, this is a lit. Now, see this burning? It's actually burning, okay? Now, you don't want a burning spill to go into this flask in a minute. You want what's called a glowing spill. So watch me carefully. Can you see it's glowing? That's a glowing splint, a glowing splint. That's what we want for this experiment. We do not want a live flame in this experiment. So blow it out after a second so you've got a glowing spill. So if I can see that on a couple of your screens, that would be great. You just want a glowing spill. Yeah. So once you've got a glowing spill, perfect. Nice one, Jake. That's looking lovely. Then you put your 1 small scoop of manganese oxide. I've managed to spill quite a bit of that on my board. That's perfect, Amelia. That's lovely. Yeah, Isabella, Uriah, yeah. And then put that into my flask. And you can see there's an immediate reaction and a lot of gas coming out, look. And if I put that in... Oh, hello, question?
Ours isn't producing gas and isn't relighting that splint. Is it because our hydrogen peroxide is too weak?
Jake, that's a beautiful observation, and very likely, yes, indeed. Did it foam up and be very react? That's perfect. That's a glowing spill. That's perfect.
No, it's not.
That is almost certainly to do with the fact that your peroxide is Isabella, perfect. So put the spill in.
No. Just blow the spill completely. Yeah.
So here, if I just bring this up to the camera for everybody. In fact, what I'll do is I shall change camera position for everybody. I think it's probably better in this view. So if I put this in, so my glowing splint, look, and into my flask, can you see? Then it really comes alight. So this is the test for oxygen. If you put a glowing spill, there's no flame on this, look. If you put a glowing spill into oxygen, it bursts back into light. It bursts back into light. And one small thing I should have said before is you don't do this with your gloves on, okay, because you've got something lit, but I have done, so I've been a bit naughty. So here, look, it bursts back into light. And from a different perspective, just so people can see it on the table, I shall do that like this. So here, look. See, glowing splint, and then it bursts back into light. Okay, I think there's a couple of questions because Ram, Prashir, how does hydrogen peroxide and manganese oxygen make pure oxygen? I'll explain that. I think I should open up some questions now. That's looking good, Dylan. That's looking good, Ella. Mackenzie, how are you doing, Mackenzie? Looking neat, excellent, cool. Just check a couple of others. I can see a couple of others. Nicholas, how are we doing? Nicholas, you done? Kuon, Lee, excellent, fantastic. Okay, I think probably, right. If I just explain a little bit of the chemistry that's going on here. So here, this chemical here is hydrogen peroxide, so it's H2O2. So it's like oxygen, it's like water, but it's got extra oxygen in it. And actually this chemical compound, H2O2, is not a very happy chemical. Okay, can you do it with the lights off, please? Ella, there's too much light coming on here at the moment, so because the sun's coming in, I can't change it. I don't want to shoo the sun away. But if you guys and girls are in your own homes, you've got to shut your curtains and dim the lights. It's a really good idea to do that. For those people who are struggling a little bit, the reaction in your flask should be very, very violent. It should produce lots of bubbles. If it's not producing lots of bubbles, put more of the peroxide in. The amount of manganese oxide is irrelevant. It just needs to be that one small scoop because there's more than enough to do the job in that case, okay? Is that all right? So what's actually happening is the manganese oxide is acting like a catalyst. And what a catalyst does is it looks at, for example, in this case, it looks at, how are we doing, Martin? Are we good? Cool, excellent, excellent, excellent. Yes, that's lovely, lovely. You might want to slap a little bit more. You can put a little bit more peroxide into there. Put a little bit more peroxide solution as well, if you like. So what's actually happening is the manganese, this dark powder. So this dark powder, what it does is it comes to the surface of the hydrogen peroxide molecule, and it goes bang, and it causes the peroxide molecule to split apart, turning it to water and oxygen. So it frees up the oxygen gas that's bonded to the H2O2. So it's what's called a catalyst. It's what's called a catalyst. So it just splits it up. So the molecule's not very stable. In fact, if you have this bottle of peroxide, if you leave it in the sunshine, for maybe half a day, you'll find that the bottle swells up because the molecule itself actually breaks down normally and produces oxygen. Okay? You're right, it works. So would it happen if you put the splint in the liquid solution? Eunice, that's a lovely question. Yes, it would not work. If you put the spill into that liquid, it will simply, because most of that liquid is water, it will simply dampen the spill, and that will be the end of that. Is that okay? Any more questions? Harrison, yes. Harrison. Any questions? Jake, it worked perfectly. Excellent.
Yeah, is it meant to slowly hiss? Is that correct?
Yes, of course. Oh, yes, absolutely. Yeah.
Just checking.
Yeah, no worries at all. Absolutely.
It's like silent. It's like a hiss.
Yeah, absolutely. Yeah.
Yeah. Good.
Any questions? Yes. Eunice, go for it. Eunice.
So what would happen? Hello, can you hear me?
Yes, I can. Yeah, Eunice, go for it.
So what are the gas molecules made up of then?
It's pure oxygen. What's coming out of it? Well, actually, that's a little bit of a fib. Because that reaction, if you feel, can everybody feel their reaction vessel? Can you see it's warm? If you feel your flask, you'll see it's warm. This is an exothermic reaction, so it's actually giving out heat. It's actually giving out, if you feel that, it's giving out. It's just an exothermic reaction. And actually, that's so warm, actually part of what's coming out of that flask is water vapour. Okay, got a little bit of, not quite steam, but water vapour. But most of the gas that's coming out of there is oxygen. Yeah, next question.
So is that then poisonous to humans?
Oh no, not at all. It's essential for humans. So, for example, all the people that, for example, maybe who've suffered badly with COVID, when they went into hospital, they needed to go and have extra oxygen. So that you need, because one of the problems with the COVID virus is that it affects the lungs to reduce the lungs capacity by filling it up with partly with liquid, and you need the extra oxygen in there. So oxygen is essential for life. Yeah.
But I meant the water vapor. Isn't water vapor poisonous to humans?
No, it's only dangerous. Water vapor is only dangerous for humans. Well, if you breathe too much in, of course, that's not very good. But also, like, but there's water vapor. If you put your hand up, can you put your hand up in front of your mouth like this, look? Like that, palm here, and breathe out heavily. What do you feel on your palm of your hand?
Heat.
Heat, and also, was it wet?
Moisture.
So you breathe out moisture vapor, water vapor every single day, because part of the respiration processes in your cells are converting oxygen and glucose into carbon dioxide and water. So in your lungs, all the time, your lungs are fully full of water vapor, and as you breathe out, you're breathing out water vapor. Okay. Harrison, you got another question? Anybody else got any questions? Harrison, yes.
Yeah, I got a question. How do I reactivate it? Do I just add more manganese oxide?
Oh, once the hydrogen peroxide has been completely broken down, decomposed effectively, you will need to rinse out the whole of the. Yeah, just replace the whole of the flask, rinse it back out, and then put more peroxide back in, and with more manganese.
So what I do is I just empty it out in the sink, pour some water in it, add the hydrogen peroxide, add the manganese, and then just relight it.
Yep, perfect. Yep, perfect.
Okay.
And you're good to go again. Okay, cool. Abigail, yes, some questions. Yep, Abigail, go for it.
I got a question. So we have to put the whole bottle for it to work, because when we put a small side, nothing happened.
Yes, sometimes some of the kits have the peroxide solution in. So if you have a box with a peroxide solution already in there, you have to dump the whole of that peroxide bottle into your flask with one small scoop of the manganese oxide solid powder, small scoop. Okay. And you might find that reaction takes place quite quickly, which is why I said that you should have your spill, your glowing splint, really at hand. Blow it out and then put it in, and it should be okay. Now, don't worry. If it doesn't work, because sometimes peroxides are this liquid is a very unstable solution, and in small quantities it can probably degrade, sometimes some quickly. I've got somebody showing me a picture. Where is it? Uriah, yes. Yeah. Oh, if it's, sometimes that might be the whole bottle. If it's a solution of manganese oxide, it might just have the one scoop in it already, so that's fine. But, so don't have any fear. If your thing didn't work, you can buy this, buy the peroxide solution either online or Amazon or just down from your local pharmacy, okay? It needs to be about 3% or 6% vol. You measure it in strength called vol, okay? And then you can add your manganese oxide to it, and it will produce plenty of oxygen. And another tip for you. If your manganese oxide doesn't work and you've got some fresh hydrogen peroxide, just get a fresh potato, chop the potato up in little tiny chunks, maybe about a tablespoon, teaspoon of potato in tiny little tiny chunks. Put the potato into your flask and then your peroxide solution into the flask as well, and potato will do the same job. Okay, little bit of magic for you if you want to take that a little bit further. And the reason being, of course, is that the potato has an enzyme in it which works the same way as manganese oxide and breaks up the hydroxide, because in all of our cells, we have hydrogen peroxide in all of our cells, not the same concentration and not the same volume. But our cells every day produce hydrogen peroxide, and it needs to be broken down. And so one of the enzymes in potatoes does that as well. Any questions? Any more questions? Or can I?
So I have a question. What is magnesium? What
Manganese.
does this contain?
It's called manganese oxide. So if you look here, can you see on your periodic table? You've got don't forget it. Don't confuse it with magnesium, which is Mg. This is manganese. I know it's got a G in the name, I know, but it's MnO. So manganese oxide is an oxide of the metal manganese. Okay. Is that okay? Any other questions? You guys, you can ask loads of questions. Yes, Jake. Ask to mute. Yes, you're on mute, Jake. Any other questions? I'll switch my lights back on, actually. I can switch my lights back on. Hello? Yes, questions? Yeah, Super Black Family, ask to mute.
Why does manganese have peroxide next to it?
No, IV.
IV next to it.
Oh, that's a fantastic word. So IV, what does IV stand for in Latin? So if you in Latin, in the alphabet, you've got 1. So remember, numerical 1 is 1. In the Latin Roman numeral, it's 2, and then 3. And what's 4? Remember. Here's a little joke. Here's a little joke for you. Okay, a Roman soldier goes into a bar. A Roman soldier goes into a bar and says, "I'll have 5 beers, please." Now he's not swearing at the bar, but that is 5 in Roman numerals. Okay. So the 4, so V and 1 is 4. So this is manganese 4 oxide. Now, to explain that, when you look at manganese, each of the elements has different party hats. If you think about it, different party hats. Sometimes they can go, I can go to 1 party. And some of the elements can go, I can go to 2 parties. And sometimes they go to 3 parties. Depending on who they're reacting with, some of the elements can change their clothes a little bit, and they can react in different ways because of the different, what are called valency states. And that just means what kind of a party I'm going to. And you do know this because, of course, in your blood, you've got hemoglobin, and that's iron. So you know that iron's in you need lots of iron in your diet, and iron's in your hemoglobin, and iron has got lots of little tiny states. It's actually in a 6 state in your hemoglobin, okay? So it's got lots of little party hats. Is that okay? Hopefully that's answered your question. You're up. Okay, any other questions? Jake?
Dan?
Yes.
Dan?
Yes, got you.
Why aren't you here on Saturday? It must be a special occasion.
It's kind of a special occasion. So let me, a little insight. This special occasion here is that I'm 50 next week, and the COVID variations mean that we can go and meet friends and family next weekend. So Mel has kindly given me a couple of weekends off to go and see friends and family and have a birthday. Thank you. That's next weekend. Cool. Mackenzie. Yes, Mackenzie. Asked to mute. Mackenzie, go for it. Mackenzie, you got to unmute.
Is it true that there...
I can't hear you. Sorry, Mackenzie. I can't hear you. I can't hear you, Mackenzie. Sorry. Sorry. I'll come back to you. I'll come back to you. Ram.
How does lactose react with the calcium hydroxide in the experiment?
That's a lovely question. It's quite a complicated bit of chemistry going on there. But do you know, have you heard of acids and alkalis?
Yeah.
Okay, so the calcium hydroxide that we used, what is that an alkali or an acidic substance?
Alkali.
It's an alkaline substance. Fantastic. So we put the alkaline substance, we changed the quality, the nature of the liquid. So we've raised the pH. Okay, and when you raise the pH in this particular reaction, you allow the reaction to work faster than if it was in an acidic solution. Is that okay?
Yeah.
So you allow that exchange of electrons to take place slightly faster. Cool. Any other questions? Yes. It's all gone very quick.
I've finished with my thing. Should I just do the same thing as earlier and just wash it out?
Yes, of course. Yeah, absolutely. With all of this equipment now, with all of the things you've done, if you just now, particularly with this manganese, you might have noticed that the manganese oxide is a very fine powder and it tends to stick to everything. Okay, so if you just give that a good solid rush out, with actually ideally with a little thin brush inside your flowers, and with warm soapy water, perfectly fine. Give it lots of rinses. As with everything in chemistry, lots and lots and lots of rinses, okay? And that will clean that out. If you've spilt any of the manganese oxide powder, you'll find you need to give that another rub around well with lots of soapy water, and that's perfectly fine. Is that okay? Don't forget copper. Copper citrate. Copper citrate. Right, for those of you guys who were here yesterday and you want to see the copper citrate, if you give me 3 seconds, I will just show you the end of the copper citrate reaction. Just give me 3 seconds. If you guys that have not seen this and don't want to hang around, then I wish you a wonderful rest of your weekend and a fantastic week ahead. And I will see you then in a couple of weeks' time. Okay, guys and girls, thank you very much for attending. Thank you very much. For those who want to hang around, it's all gone nuts. For those of you who want to hang around, please do hang around, and I will see you in a couple of weeks. In a couple of minutes. But for those who are not going to do the copper one with me, then I will see you in a couple of weeks' time. Thank you very much for subscribing to MEL. So copper, just give me 3 seconds to get it back into play. Okay, 3 seconds. Right, another couple of seconds. Hang on. If I just get rid of that one, and I need some tin. Right, so with your kit, hopefully, if I just change my camera angle a little bit, I'm going to change it to bird's eye view. Bye, Amelia. Bye, George. Bye, Amelia. Bye, Ella. Right, so you should have from your copper yesterday. Some nice blue powder. Has everybody got their blue powder, their copper citrate? Everybody got the copper citrate? Yeah, you've got the copper citrate, fantastic. Right, so all we're going to do with this one, just quickly change that. Harrison, you're very welcome, Harry one. Okay, so what we're going to do is we're going to use some little tin, your little tiny cake tin, and I'm just going to get one of those. Right, so if you place, look, not that one, I think, who's that? Addy, not that one. This is for students who were doing the copper yesterday. If you basically put your little tin, on top of your glass beaker, okay, and then get your copper citrate and pop it into the tin like that. Now you might need to give it a little scrape with a little bit of a wooden spatula, okay, so just pop that into there like that. You might have noticed, and just spread it around a little bit over the base of your, I'm going to bring this up actually, I'm going to raise this up. If you don't mind, for some people who can't see this, I'm just going to get a little tiny stand and raise it up. Okay, so give me a couple of seconds. Then move that out of there, that out of there. And now my very dirty little tray, so hopefully. Can everybody see that? Hopefully everybody can see that. Cool. Now, what you then do is just get a match and gently touch the surface of this copper citrate. So just gently touch the copper with a match, with a lit match, okay? You only need to touch it maybe in 2 or 3 places, so just touch it gently, look in 2 or 3 places. And then watch what happens. And you should see a really rather curious little tiny sparking chemical reaction taking place. Look, it spontaneously, creepily combusts. It's a very unstable little chemical. You can see it quietly springing into life. Direct message, Harrison Yen, yes. Is that okay? Has everybody got that? So when you produce the copper citrate, it had to be really, really super dry, and it takes some time to get it. Sometimes it needs a little prod and a poke, okay? Yes, Harrison.
Do I just? I was just going to ask about the water, but I've already just read the little the book thing about it.
Sure.
I'm fine. Just a question.
Okay, yeah, sure, no problem at all, no problem.
Sorry.
You're very welcome. It's a pleasure. And what you should notice at the surface, can everybody notice at the surface it's going a kind of orangey colour? It's because when copper citrate decomposes, thermally decomposes, nice one, Jake, excellent. That's actually metallic copper. So the sodium citrate breaks down into copper metal, which you can see here, and that also partly oxidizes, which is why it goes a little bit black. But you've also got water vapor coming off and carbon dioxide coming off, okay? So there's a little sparks is when the sodium citrate breaks down and produces a little bit of copper, well, produces quite a lot of copper actually, and then water and then a little bit of CO2. And sometimes you might want to give it just a little prod because there's some unreacted on the bottom of it. How lovely is that? Is that right? Cool. So, a little joke. Any questions? Any questions for you guys? I will just change screens a little bit. Any questions? No? Harrison. Oh, Louisa. Louisa. Go for it. Louisa.
Okay. So what chemistry was in that?
Oh, so in this pot that I had is a chemical compound. You can see the residual blue bit of it. So in the copper box,
Yes.
when you get the copper box, it's called copper citrate. So you know when you've had citrate, have you ever had a lemon or an orange or anything like that? Have you?
He's asking.
Yeah.
Yeah. So those plants, like a lot of plants actually, contain citric acid, okay? But oranges and lemons also contain ascorbic acid, that's vitamin C, but they contain citric acid. And so effectively what happens is if you react copper by way of a little root, you can bind it to citrate to make copper citrate.
And you put citrate together. You can put that together.
Effectively bind citric acid with copper. And what I've done here is a very unstable compound, thermally unstable. So if you give it a little poke, it then goes, oh, I'll decompose then. And so it comes apart and the CO2 comes off and the water comes off. That's the citrate molecule breaking down.
Okay.
And it leaves metallic copper, a little bit oxidized in the bottom of the pan. Is that okay? Cool.
Yeah.
You're very welcome.
Okay, ask you, where'd you got cylinders, those chemistry tubes, where'd you got them from?
Oh, these the little reagent tubes, the little reagent bottles, they're specially manufactured for MEL. Okay, so they're specially.
MEL Chemistry kit for next year. He's 7. He's going to turn 8, and he's interested in chemistry.
Awesome.
He loves it.
Chemistry is amazing. It's the most amazing subject going, I think. And then physics is great, and biology is good, and geology is super too.
I'm gonna go to physics.
You're going to do physics? Okay.
Cool.
Thank you.
You're very welcome. It's a pleasure. Jake, go for it.
Thank you for a brilliant lesson today, Don. It was really good.
It's an absolute pleasure. I'm delighted. It's so nice to have you on, Jake, as it with all the students, but it's lovely to have you on particularly. Love your enthusiasm and experiment a bit more. There's a couple of tricky, quirky questions with that copper citrate. So I shall see you again, hopefully in a couple of weeks' time. So thank you very much.